For decades, 3D modeling and realistic simulation technology have been used in the automotive, aerospace, energy, high-tech, and many other industries to virtually design and test products that we interact with every day. So, what if we achieved the state whereby doctors could rely on the same technology for improving patient care? The Living Heart Project, formed by Simulia, the Dassault Systèmes brand for realistic simulation, set out to answer this very question. By relying on the powerful 3D experience platform and crucial input from leading engineers, medical professionals, and regulatory bodies, the project seeks to revolutionize patient care by utilizing these groups and technology to translate research discoveries into proven treatments. During this experience, we will take you on a journey into the future of medicine, where physicians and surgeons will use advanced digital technology, such as dynamic 3D modeling and realistic simulation, to treat patients. In the future, we can imagine medical practitioners interacting with virtual patient models to perform non-invasive diagnostic studies. These advancements will enable the exploration of entire biological systems of an individual patient. In this next sequence, let's imagine a cardiologist having direct access to the cloud-based 3D experience platform to compile diagnostic data, capture macro measurements in the heart to apply range specifications, target markers to capture micro movements in the heart, personalize a realistic human heart simulation using the gathered diagnostic and measurement data, analyze the behavior of the patient's simulated heart to identify potential concerns, collaborate with other experts to explore treatment scenarios and search critical studies, and finally, simulate a variety of treatment scenarios to identify the optimal outcome for the patient. The potential for this technology is immense. For instance, here is an example of a realistic simulation of a healthy adult human heart. Personalized patient models, based on measured heart data, can be validated against the performance of this healthy heart model for unprecedented insight into defects or future complications. This technology will also enable cardiologists to perform deep, non-invasive studies to explore the behavior of a patient's heart. Let's take a moment to study the interior of a beating human heart, with remarkable horizontal and vertical cut views. In this example, we can visualize the electrical potential and the mechanical deformation across the human heart throughout its cardiac cycle. The last model we will study is what we refer to as the fantastic voyage of blood flowing through the heart. First, we will enter the heart through the superior vena cava, emptying oxygen-poor blood from the body into the right atrium of the heart. As the atrium contracts, we move from the right atrium into the right ventricle through the tricuspid valve. When the ventricle is full, the tricuspid valve shuts, and prevents blood from flowing backwards into the atrium while the ventricle contracts. As the ventricle contracts, we leave the heart through the pulmonic valve, into the pulmonary artery and to the lungs where it is oxygenated. Now we return to the heart by way of the pulmonary vein, which carries oxygen-rich blood from the lungs into the left atrium of the heart. As the atrium contracts, we move from the left atrium into the left ventricle through the mitral valve. When the ventricle is full, the mitral valve shuts. This prevents blood from flowing backward into the atrium while the ventricle contracts. As the ventricle contracts, we leave the heart through the aortic valve and proceed into the aorta and to the body. We hope that this journey has inspired you to learn more about the Living Heart Project. For more information, please visit 3ds.com/heart.